Good evening, everyone. I am Suchir Mamidala, a student at IIT Madras, currently working as a summer intern at Maritime Research Center, Pune. So, today I'll be talking about an increasingly important topic, which is on digitalizing the process of marine biofouling with a focus specific to the tropical environments. So, what is biofouling? Biofouling refers to the unwanted buildup of organisms like bacteria, algae, barnacles on the submerged surfaces such as ship hulls, pipelines, sensors, or offshore rigs. It starts with microfouling, where microorganisms form biofilms, and evolves into macrofouling, where larger organisms like barnacles and mussels take over. This buildup increases friction and drag, especially on ships, leading to higher fuel consumption, greenhouse gas emission, corrosion, and even sensor inaccuracies. Several interacting parameters control how, where, and how fast this fouling occurs. First, temperature and nutrients drive the organism growth. Salinity influences which species thrive. Some prefer seawater and others prefer brackish or estuarine zones. Then we have the hydrodynamic conditions. The fast flowing water may prevent settlement, while stagnant areas like the propeller region promote it. The surface itself matters. Rougher or degraded coatings allow easier addition. Even water pH and the oxygen levels influence microbial activity and species composition. So the tropical region between the Tropic of Cancer and the Tropic of Capricorn is highly prone to biofouling due to the warm waters and nutrient-rich coasts, which accelerate organism growth. Falling rates can be 2 to 3 times higher than in the temperate zones, with Indian ports reporting up to 19 kilograms of 19 kg per meter square of biomass. For vessels, this can mean 40% more fuel consumption and a 72% higher CO2 emissions, making tropical biofouling a critical issue for cost and sustainability. Traditional fouling management techniques is very reactive, so waiting for buildup and then trying to clean them, leading to high costs, delays, and damage. Manual inspections are slow, inconsistent, and often impractical. Digitalizing the process with real-time sensors, machine learning, and remote imaging enables predictive maintenance, detecting fouling early, optimizing cleaning, and avoiding performance losses. In tropical waters, where fouling is faster and more intense, real-time systems can cut fuel costs, lower emissions, and reduce harmful chemical use. In essence, digitalization makes fouling a manageable, data-driven challenge. So the current literature on the fouling simulation mainly includes two types of categories. One is the physics-based CFD, computational fluid dynamic models, and the other one is the data-driven AI models. So the existing CFD models simulate how biofouling develops in different marine applications, from heat exchangers to tidal turbines. They account for parameters like wall shear stress and turbulence. However, most of these models are validated in the temperate or industrial settings and are not very well adapted to the tropical conditions. On the AI side, models like the CFD-ANN hybrid or the Sundar's deep learning framework have shown impressive predictive accuracy. But again, these models lack real-world data from tropical marine zones. The LSTM, long short-term memory models, show promise for time-based predictions, but are yet to be deployed in high biodiversity coastal areas. The field studies provide vital biological insights alongside modeling. The PVC settlement plates and environmental DNA, also called as eDNA, sampling have been used to detect invasive species in tropical waters. Deep learning has also shown promise, classifying biofouling severity in 10,000 plus images with 90% expert agreement. However, these studies often lack tropical representation or sufficient resolution. underscoring the need to integrate them with modeling tools to build robust predictive platforms, especially for tropical digital twins. Creating a spatiotemporal map of tropical biofouling faces key challenges. First, data scarcity is a major hurdle. Unlike Europe, tropical regions lack dense continuous monitoring. Fouling occurs year round, yet tools like eDNA and settlement plates are not widely deployed. Second is the ecological complexity is very high. Diverse species like coral associated organisms and shipworms respond to local stressors such as runoff and microplastics. Interspecies dynamics vary with factors like wave exposure, which are rarely tracked. Lastly, the technological barriers still remain. Sensors struggle in turbid waters, and scaling them for CFD or ML models to basin levels is often computationally unfeasible. These gaps highlight the need for tropical specific digital infrastructure and approaches. So, in this phase of the digitalization project, I'm currently trying to adapt a temperate zone CFD model for using in the tropical regions in the Indian subcontinent, where factors like biodiversity, water temperature, and fouling rates differ significantly. The Kochi coast is chosen as the pilot location due to continuous monitoring by the Indian National Center for Ocean Information Services and also the support from nearby regional marine institutes like CMFRI, which is the Central Marine Fisheries Research Institute, enabling robust data collection and validation. The aim is to retrain and recalibrate the existing model using regional data to accurately simulate tropical fouling dynamics. The way forward and the future prospects in tropical biofouling simulation lie in building integrated, data-driven, and predictive systems. First, we must try to rebuild the data infrastructure. Community-based monitoring through local fishers and divers can enhance coastal data collection. Blockchain can ensure secure and transparent data sharing, while low-cost sensors and AUVs equipped with anti-fouling tech and eDNA samplers can improve tropical data capture. Next, the existing CFD-ANN and LSTM models from the temperate regions can be adapted via transfer learning, incorporating tropical specific factors like coral interactions and monsoon dynamics. Field validation will ensure accuracy and robustness. This integrated approach will enable precision biofouling management where it's needed the most. Thank you.